Okay, let's continue our last example. I have signal frequency of 10 Hertz. I also have sampling frequency of 12 Hertz. So the question is, do we have aliasing? Also, if yes, what is the alias frequency? Let me enlarge this a little bit. Looks like it's too small. So this means if you remember last time, we said if signal frequency is smaller or equal than the Nyquist frequency, which is equal to sampling frequency divided by 2, and there's no aliasing. So in this case, we have sampling frequency of 12, so Nyquist frequency 6 Hertz. Signal frequency is 10 Hertz, which is greater than 6 Hertz. So we do have alias effect. So this means if I have a signal, sinusoidal signal at 10 Hertz coming in through this FFT, supposedly I should get from the frequency spectrum, I should get a spike at 10 Hertz in frequency domain. However, because of these small sampling size frequency, I don't get that 10 Hertz. That's why we call alias. And the question is, what is the frequency which is wrong? So you get these frequency, you still get the signals, but what is this frequency? Okay. In other words, from 10 coming in time domain through FFT to frequency domain, you should get 10. So there's no alias. No alias. However, because in this case our sampling frequency is too small, and we will get the alias. And the question is, what is the frequency that misrepresent this 10 Hertz? Okay, and then we will use so-called folding theory to determine this. So what's folding? So we know there's no signal frequency smaller than Nyquist frequency. this is no aliasing. So meaning the ratio Nyquist should be smaller than 1. Okay, so we make this ratio. So make a sawtooth plot ranging from 0 to 1. So these values represent the ratio of signal frequency over Nyquist frequency. Okay, so between 0 and 1, there's no aliasing. So we call this folding. One to two. Two, three. So whatever value of these ratios greater than 1, then it will be between 1 and 2 or 2 or 3. So this one, the value will be folded back to 0 and 1. If I have a ratio right here, it will fold back to 0 and 1 range, which is this point right here. Will give us so-called the alias over the Nyquist frequency in terms of ratio. Okay. Let me zoom a little bit. Okay. So if you have ratios, the real ratio is between 2 and 3. Let's say this point, 2 and 3, it will fold back to 2 and 1, this point, and between 1 and 2, and will fall back to 0 and 1 will be this point, and this will be the alias frequency located. Okay, so if we have this, let's put our number on last examples. So frequency is input signal frequency is 10, Nyquist is 6. So signal frequency to Nyquist frequency ratio should be 10 over 6, 1.66. So greater than 1. So of course there's aliasing. So let's use the folding theory. 0 and 1, 1 and 2. So right now 1.6 is right here. So it's symmetric about this horizontal line. So this one will fall back to 0 to 1 range. So it will be right here, which is 0.33. So now the alias, the ratio of alias frequency to Nyquist frequency is 0.33, and the alias frequency we can find is 0.33 times Nyquist frequency 6, which is about 2 Hertz. In other words, $10 kilohertz coming in through FFT because of the small sampling frequency 12. We don't get 10 Hertz on the scope, the analyzer, but we do get a signal at 2 Hertz, which is what we referred Alias frequency.